I'm glad I didn't understand it because I'm sure it was full of exaggerations. Okay, so I want to give somewhat of a survey talk today, and that's on certain phase transition problems. When I say phase transition, I mean spatial phase transitions, and their relation to the calculus of variations. So the simplest such problem is perhaps an Allen-Kahn model. And so this models phase transitions in a bitalic metal alloy, and the sort of PDE that arises here has the form minus the Laplacian of u plus g prime of u equals 0. The function g is a double well potential, so it looks like this. And the simplest example would be, say, something like g equal u squared times 1 minus u squared. And from that equation, we see that u identically 0 and u identically 1 are solutions of this equation. And they're what are called the pure states. And one is interested in what's called a mixed state. That is a solution that lies between 0 and 1. And it's not difficult to see there are lots of solutions like that. Oh, say here we're working in Rn or R2, whatever. And it's easy to see that if you choose any direction in Rn, you can look at the corresponding ordinary differential equation in that direction. And you can even write down explicitly for this special case a solution which will have the form. So here's 0 and 1. And the solution will, if we were looking in, say, the x1 direction, the solution will go from asymptotically from 0 to 1 in that direction. Okay, so that's the mixed state for this particular case. It's not unique. You can shift it. And as I said, it exists in any direction you choose. More general sort of Allen-Kahn model is, say, minus Laplacian of u plus a of x times g prime of u equals 0. So let's allow some spatial dependence in the problem. The function a, say, will be positive. Smooth function. And the simplest case would be to take a to be periodic in all of its arguments. Okay, so it's here you can't write down a solution explicitly, but you can show that the same sort of solution exists. That is a solution if, let's say, there's a solution in the which just depends on as a function of x1 goes from 0 to 1 as we run from minus infinity to infinity, and is the same. Well, unlike the previous case, you can no longer shift the solution in an arbitrary fashion, but since A is periodic in its variables, then you can shift it by an integer. So in this case, u of x plus j times a unit vector in the x1 direction would also be a solution for all j belonging to z. So there's no longer a continuous family of solutions, but this discrete family of solutions. Okay. You could still more generally, you could take a function of the form g sub u of x and u, the partial with respect to u, where again it has the same sort of g has the same sort of qualitative behavior. Now, this class of equations, in fact, turns out can be viewed as a special case of another class, which I'll call PDE. And these equations have the form minus Laplacian of u plus f sub u of x and u equals 0. That's the partial of f with respect to u. And here the function f is, say, C2 from Rn cross R over Zn cross Z, by which I mean it's periodic in each of its arguments into R. Okay. This equation is actually a very special case of a class of equations that was introduced by Moser. Moser was interested in giving a version of Aubrey-Mather theory for PDEs. Now, Aubrey-Mather theory arose in trying to study certain stability questions for Hamiltonian systems of ordinary differential equations. And Aubrey and Mather looked at, in that regard, looked at certain questions of self-maps of an annulus into itself. But I don't want to get into that. In any event, Moser was interested, introduced this equation to try to develop a PD model, a PD version of such a theory, and was interested in a special class of solutions of this equation. This equation looks rather different from the Allen-Kahn model that I wrote there, because there you have a double well potential, and this f is just a periodic function. It's rather different behavior. But in fact, you can reduce the study of this, in a sense, to the study of this in the following fashion. Take the function g and say this is 0 and 1, and let's truncate it at 0 and 1, and let's repeat it periodically. Then it will be of the form of the f that we have here. And then what you can show is that there are solutions of that periodic problem which lie between 0 and 1. And any such solution is then a solution of the original equation. So one can view the study of these problems, or a more general class, as a special case of a study of this sort of model. And so I'm going to work in the framework of this model. Okay, so by the way, I should mention one example that you're all, I'm sure, familiar with of this. If you take the simplest case of here again we have x in Rn. If we take n equal 1, this just becomes minus u double prime plus f sub u. Maybe I should write t instead of x to make it look more familiar. So this is just a version of the forced nonlinear pendulum equation. Okay. Okay. So if we want to study phase transitions in this sort of setting, well, what are we transitioning from? In the Allen-Kahn model, we're going from 0 to 1, and the analog here is we'll look at, for PDE, we'll look at periodic solutions. Okay, and such solutions were studied by Moser, and what he showed is there are indeed lots of such solutions, and the way you can show that is just an elementary argument using the calculus of variations. Namely, associated with PDE is a Lagrangian let's call that L of u. And let's look at the integral of L of u over, say, the unit cube in Rn, or equally well, you could look at this on the n torus with period 1. Let's give this a name, call this J0 of u. So now if we minimize the themum of J0 of u for u's which are, well, have square integrable first derivatives and which are periodic in all of the variables. So minimize this, and let's call this C0. Then it's easy to see, or it's easy to use elementary variational arguments to show that there exist minimizers for this problem. And we can call M0 is the set of minimizers okay, so M0 is non-empty. And any member of M0 is going to be a periodic solution of this equation. So that's a very elementary fact. And likewise, because of the special form of the function f, whenever u belongs to M0, then if we add an integer to it, this also belongs to M0. So solutions occur in such families. And another interesting fact occurring here, as was shown by Moser, is that M0 is an ordered set. Okay. It's also elementary but not so obvious. And that means that, well, if we look at the graphs of the members of M0, either the graphs fill in all of Rn plus 1, or there are going to be gaps in Rn plus 1. So the more geometrical way to say that is either we have a foliation of Rn plus 1 or merely a lamination. And so in the latter case, which is sort of the generic case, then there'll be gaps between parts of M0. And whenever we have such a gap, then the associated pair of functions we'll call a gap pair. So this is a pair of members of M0 with no other members of M0 between them. Okay. And now, so V and W are essentially playing the role of 0 and 1 in the previous Allen-Kahn model. And we're interested in solutions that will transition from V to W. So solutions that are heteroclinic from V to W. That, for example, as x1 tends to minus infinity, they'll approach V. As x1 tends to infinity, they'll approach W. Okay. So that would be an example of a transition type solution, a phase transition type solution. And do there exist such solutions? Well, one can try to do for this setting exactly what we just did. Why not take our Lagrangian and minimize it over the class of candidates for such solutions? Well, what's a natural class of candidates for these solutions? What we might do is, say, take gamma 1 of VW is the set of functions U which have some sort of regularity property, and the technical way to say it is say they belong to W1, 2 loc on R cross Tn minus 1. So I want them to be periodic in x2 through xn and locally squareable in x1 such that they lie between V and W, and they have the asymptotic properties that we want. They approach V as, say, x1 tends to minus infinity and W as x1 tends to infinity. There are lots of different ways we could express that analytically. One convenient way is to say, let's take R cross Tn minus 1 and break it up into unit pieces. So here's Ti. Ti is equal to I plus 1 cross Tn minus 1. And then we can require that, say, the norm of U minus V, L2 of Ti goes to 0 as I tends to minus infinity, and the norm of U minus W, L2 of Ti goes to 0 as I tends to infinity. So we have this mild asymptoting to the states V and W, the periodic solutions V and W. And now we can write down the associated functional. So let's take say the integral over R cross Tn minus 1 of our Lagrangian. And we'll try to minimize this over our class of functions gamma 1 here. But immediately we're going to get into trouble. For example, remember what L looks like. Suppose F is bounded from below by a positive constant. Then we're integrating this expression over an infinite region. So for every member of our class gamma 1, this will be infinite. The functional will be infinite for all admissible functions. So we're immediately in trouble. And what you have to do is to renormalize the problem in some sense. We have to subtract off that infinitude. And how do you do that? Well, there's no recipe for doing something like that, but one way that works here is to do the following. Let's define our renormalized functional J1 of u and let's take that to be the sum of the integral over ti of L of u minus C naught. I'm going to subtract off this minimization value associated with the members of the class M naught. And we'll sum this for I and Z. And it turns out that this functional has some nice properties. I mean, it takes a little bit of work to show this, but in particular, this is bounded from below. Which is, of course, crucial if you want to minimize the functional. It better be bounded from below. If it's if J1 of u is finite for some u, that implies that the norm of u minus v, W12 of ti, converge to 0 as I tends to minus infinity, with an analogous statement about the behavior as it approaches plus infinity. So the asymptotics come out immediately in that sense. And thirdly, it turns out that there's also some kind of compactness property. If you know the language, there's a kind of Palais-Smale property for minimizing sequences. Now, I don't want to state it explicitly, but it possesses some nice compactness properties. So in particular, we can define C1 of VW to be the infimum of J1 of u for u in gamma 1 of VW. And one can show that there exist minimizers. Okay, here's our minimization problem. And if we let M1 of VW equal the set of u in gamma 1 such that J1 of u equals C1, then again, this is non-empty. Any u in this set is a minimizer, is a classical solution of our equation. So this provides us with these transitional solutions that I just mentioned. Moreover, remember I said that Moser showed that the set M0 is an ordered set. Well, it turns out that the same sort of argument he used applies here, and this too is an ordered set. So if you take any two members of this set, either they're identical or one of them is bigger than the other. Okay, so we're in the same sort of setting as we were before. Either the region between V and W is foliated by the set of solutions of this equation, or not, in which case you can find gaps. So again, the picture, here's V, whoops, here's W, here's V. So if we have a gap, then we'll have an associated gap pair here. I should mention, at this point I should mention the work of Victor Bongert. Okay, so Bongert had another approach to the existence of these solutions. He didn't use a minimization argument. He used another argument based on some other things that Moser did. And in addition to that, he studied these more complex situations and showed, well, suppose that you have such a gap pair, V1 and a W1 of heteroclinics between V and W. And then he showed that there exist additional heteroclinic solutions. There exist solutions that, as a function of x2, are heteroclinic from V1 to W1. Okay, in other words, there's a function, say capital U, such that U tends to, x tends to V1 of x as x2 tends to minus infinity, and it tends to W1 of x as x2 tends to infinity. Okay? And he used the same sort of argument to prove this that he used to obtain the original heteroclinics. It turns out that once again you can use a minimization argument to find these more complex solutions that are heteroclinic in x2 by a similar argument to the one that I used here. Now, instead of integrating something over r cross Tn minus 1, you'd want to integrate over r2 cross Tn minus 2. But you're going to have a similar problem of functionals becoming infinite, so you have to make a second renormalization. There's a second renormalized functional. So. And you can do that in the same spirit of what I showed you here. Remember, we started out by breaking up r cross Tn minus 1 into pieces. Well, let's do the same thing with r2 cross Tn minus 2. So we'll think of the plane, and we'll break it up into strips. Say here's Si is the ith strip, and then the second renormalized functional will just be J2 of U equal the sum for I and Z of J1 of U restricted to Si minus C1 of VW. Here's our renormalization. And exactly the same sort of arguments that work for J1 work for J2. It gets a little more complicated, but it's the same spirit. Okay. And likewise, you can continue in the same fashion. This has a set of minimizers, which is going to be an ordered set, etc. Okay. Well, now we can look. We have heteroclinics, more complex heteroclinics. What about other kinds of solutions? Well, at this point we can use some ideas from dynamical systems and the calculus of variations. Namely, we can do some gluing and shadowing. Okay. Well, what do I mean by gluing? We have solutions that look like this. And by the same, so these are heteroclinic from V to W. By the same token, we can get solutions that are heteroclinic from W to V. So you might say, can we, in some sense, formally glue these together, whatever that means, and get a solution? So that looks like that. Okay, this would be a solution that's homoclinic to V. It's asymptotic to V as x1 tends to plus or minus infinity. Okay, and one can do that. Oh, so that's the gluing part. Shadowing, well, what do we mean by that? So that's a term from dynamical systems. So in some sense, can we find an actual solution of the equation which is homoclinic to V and which on some semi-infinite region is close to one of the solutions we found of this type, and in the semi-infinite region is close to a solution of this type. Okay, where close can be measured in various norms. Okay, and it turns out you can do that. The solutions that we found, I'm just about to lose a microphone here. The solutions that we found here were obtained by these minimization arguments. We minimized J1 here. So in some sense, our basic heteroclinic solutions are global minima. Now we can find these more complex solutions as local minima. So and I don't want to go too much into the technical details of doing this, but the idea is roughly to impose a set of constraints on our class of admissible functions. So we're interested in a solution that looks like this. So let's draw our picture again. And in a large region here, let's require that our admissible functions are close to the function V. And in some large region here, we'll require that they be close to W, and again close to W, and finally close to V. Okay, so an admissible function is going to look something like this. So it's roughly going to have the form that we're interested in. And now we can minimize J1 on such a class of functions. And you can show that there's a minimizer But since we have a constrained variational problem, a minimizer may not be a solution of the equation we're interested in, because maybe the minimizer touches the constraint set. And if it touches the constraint set, if you know a little bit about the calculus of variations, it can have a kink there. There can be some sort of discontinuity in the solution, and it won't satisfy the equation at a point where such a touching occurs. So what we really want to show is that the minimizer of this problem is an interior minimizer. It stays away from the constraint set. And I haven't really imposed any further conditions on things here. And under the following sort of conditions, you can do that. First of all, we need that M1 of VW and M1 of WV contain gaps. As there are gap pairs associated with each of these. And secondly, we need that these constraints, which I haven't really described precisely, are spaced far enough apart. Is the difference, the distance between the constraint sets is large. And then, if that's the case, there are indeed solutions. There are minimizers to the associated variational problem, which are interior, which to the constraint set, which don't touch the constraint set. And then there are going to be solutions of this type of our variational of our equation. Since we can move these constraints as far apart as we like, that shows us there are going to be infinitely many different solutions of this type. Okay. Moreover, there's well, these, I should have remarked that these solutions are what you might call two-transition solutions. Okay. In contrast to the ones we look at here, which make a single transition. So they go from V to W. Here we go from V to W, back to V. Well, just as we looked at two transition solutions, you can look at solutions which have an arbitrary number of transitions. So you can look at solutions which do the following. It's a three-transition solution. And the same arguments give you three-transition solutions, k-transition solutions, and by passing to a limit, you can even get infinite transition solutions. Okay. Just to give you a simple example of this sort of situation that you're more familiar with, let's go back to the case of n equal 1 and the pendulum. So take a vertical pendulum. A vertical pendulum has a solution, well, if it's released, tipped slightly, it'll go all the way around and come back to its starting point. That corresponds to a solution, well, this may correspond to originally an angle, depending how you measure your angles. If we measure the angles relative to this, it might be an original angle of 0, and it increases, say, to 2 pi. Okay, that's exactly our one transition sort of heteroclinic solution. Okay, well, if you think of the pendulum almost reaching its vertical position and coming back again, then that means it looks like this. So that corresponds to the sort of solution we looked at here. But there's another kind of motion we can imagine also. Suppose the pendulum rotates around once, slows down as it approaches the top, and then continues for one more revolution and then stops. Well, that would be a solution. Looks like this. So that's another way we can glue solutions. Here we're gluing some solution u to 1 plus u. Okay, and see that an example of that in terms of the pendulum. So these solutions are monotone in contrast to these, but they're both two transition solutions. Okay. Naturally, well, again, there are going to be infinitely many solutions of that type, and you can continue to play this sort of game by combining the two types of solutions. So you can get a mixture of these two types of solutions. So maybe something goes like this, etc. And so you can do, in the language of dynamical systems, you can make a symbolic dynamics of such solutions. So lots of different solutions of that type. Okay. Now, I should mention some open questions. For example, gluing. So, as I mentioned before, if we have a W1 and a V1, then there's a solution that's heteroclinic, say call it U1. U1 is heteroclinic in X2 from V1 to W1. And by the same token, we might have a W1 hat and a V1 hat and a U1 hat, which is heteroclinic in X2 from V1 hat to W1 hat. Well, can we glue these two types of solutions together? It seems pretty reasonable, but that's an open question. I believe it's true. In fact, what I believe is true is a more general conjecture. Any kind of gluing that makes geometric sense should lead to an actual solution. Any geometrically reasonable gives a solution, gives an actual solution. Okay. Some other results and open questions. If you look at all of the examples that I've mentioned so far involve heteroclinics or homoclinics or whatever in a particular direction. So here we have heteroclinics in X1, heteroclinics in X1. More complex solutions in homoclinics in the X1 direction. Even these are heteroclinic in the X2 direction. So, but you can ask for more general sort of solutions. So, for example, let's go back to, maybe I'll go back here to the Allen-Kahn model. And maybe let's take n equal 2. So here's R2. And we know we have the pure states, u identically 0 and u identically 1 are solutions. And we can pose the following question. Suppose I pick some regions in the plane. Can I find a solution of the equation which shadows 1 is close to 1 in the regions I've prescribed and is close to 0 elsewhere except for a transition region? Can I have arbitrary sorts of transitions? So this is another natural sort of question you can ask. What about transition solutions of this type? And so this is a little trickier, but an Alencon model of this type was given by Jae-Young Bion and myself. Okay, within an Alencon model setting, I don't have enough time to go more into the details here, but you can do that for some special interesting special cases. You can ask the same thing for our more general setting, for PDE. So you might ask, can I find solutions which are close to, instead of 1 here, close to V, in some prescribed regions, and close to W in the complementary regions with transition layers in between them. Okay, this is totally open. Okay, I mean, take the simplest case. Can you find something which is near V here and near W in the rest of space? So that's a nice open question. And again, I don't think it will be true in the full generality of the examples we've looked at earlier. I think you may have to say something more about the behavior of your equations near V and W. Maybe you need them to be non-degenerate solutions in some appropriate sense. But my guess is that there should be result in this setting. Okay. Okay. So thus far, we've been looking at solutions which have been at least local minima of some kind of functional. You can ask, what about other kinds of critical points of functionals? Are there other kinds of solutions? And you can ask that question already in the setting of the periodic solutions. So say, let's go back. Here's a gap pair of periodic solutions. Let's think about what that says geometrically in terms of the functional. So here's V, here's W, whoops, here's W, and so what I'm graphing in some heuristic sense is J0. So our functional has minima at V and at W. So here we have a pair of local minima of the functional, which are not global minima. Okay? And when you have a picture like this, and you know a bit about the calculus of variations, you say, this is precisely the sort of picture that you have associated with the mountain pass theorem. Okay, a local min which is not a global min. And then if one has the right sort of compactness structure in your functional, there will exist a so-called mountain pass solution, another solution that you can obtain by minimaxing your functional over classes of curves that, say, join these 2 points. And it turns out you can do that here for the periodics, and there's going to be another periodic solution. And interestingly, in this setting, the solution, the minimax solution, the mountain pass solution, lies between V and W. Actually, point-wise, in the general sort of setting where you can invoke the mountain pass theorem, you don't have such an ordered structure. But here, it turns out you can get such a U between V and W. The same thing is true for a gap pair of heteroclinics. We have the same picture if I replace J0 by J1 and the V and W by V1 and W1. We have local minima. There's going to be a mountain pass solution. You have less compactness here, but you can still show there's a mountain pass solution. And once again, it's going to lie in between these two. Okay. There's some additional phenomena that occur here that don't occur, that occur with respect to the mountain pass solutions that don't occur with just the periodics. One thing that I didn't mention before is, well, our function f was assumed to be one periodic in the x1s and in u. Well, if it's one periodic in, say, the x sub i's, it's also two periodic or three periodic or k periodic. So instead of looking for solutions which are one periodic in x1, I can look for solutions which are k1 periodic in x1 and k2 periodic in x2 and so on. If you try to play the same game of minimizing over the associated family of periodic functions, you're not going to get anything new. That is, the minimizer in the class of functions which is k1 periodic in x1 and k2 periodic in x2, etc., will just be a repeat of the one periodic in each variable function we already obtained. However, if you do the same thing with the mountain pass solutions, that's no longer the case. The order structure that one has for the periodics plays a role in showing you get nothing new when you look in these bigger classes of functions. But you don't have an order structure for the mountain pass solutions. And so, in general, if you look for k1 periodics, etc., in x1, you can get different sets of mountain pass solutions. So you have, in a sense, many more mountain pass solutions than you have periodic solutions here. Okay. Another thing that you can do with mountain pass solutions is to ask, well, can you glue, say, mountain pass solutions and mountain pass heteroclinic solutions and minimizing heteroclinic solutions. So here's a mountain pass solution and here's a min. Can I glue one of these yellow solutions to one of these heteroclinics? And the answer is yes. And that was done in particular by Sergei Bolotin and myself. And likewise, Jae-Young Bion and I did it in our Alan Kahn setting. You can also study questions about the asymptotic behavior of some of these as you pull these farther and farther apart. Okay. Well, the next topic on my list is systems, but I've run out of time, so I will stop here. Thank you.